Welcome to the first introductory lecture on Chemical Reaction Engineering 1. As you know, this course is divided into two parts. One is Chemical Reaction Engineering 1, where we will discuss mostly on homogeneous reactions and ideal and as well as non-ideal reactor designs, and in the second part generally we considered heterogeneous reactions, catalytic reactions and so on. So, our course is mostly on the first part. Before going to this lecture, let us have our objectives of this course. The general objectives of Chemical Reaction Engineering 1 are to provide an overview of chemical kinetics and reactor design at basic to the intermediate level. And this course will apply the concept of reaction rate, then stoichiometry and equilibrium to the analysis of different chemicals and biological reacting systems. For example, derivation of rate expression from the reaction mechanism, or we can take the concept from the equilibrium or steady state assumptions for certain reactions. So, design of chemical and biochemical reactors via synthesis of chemical kinetics and mass and energy balances. So, this course will also consider the design of reactors which will take into account the chemical kinetics as well as mass and energy balances wherever necessary. The broad goal of this course is to provide student with theoretical and analytical background so that they can understand the chemical kinetics and the reactor design to tackle the sort of complex problem. The detailed course plan for this: in module 1 we will consider the kinetics of homogeneous reactions, and in module 2 we will consider stoichiometry. Module 3 we will discuss interpretation of the batch reactor data, and in module 4 we will consider ideal reactor design, and module 5 non-ideal reactor design. So, these 5 modules we will consider most of our topic to be covered in this course. The textbooks which we generally follow for Chemical Reaction Engineering 1, the first one is Octave Levenspiel, that is on chemical reaction engineering. The second book is H. Scott Fogler, that is Elements of Chemical Reaction Engineering, and the third one is J. M. Smith, Chemical Engineering Kinetics. In addition to that, we will have many reference books which we will highlight while we discuss different topics in this lecture series. So, the brief introduction and overview of this course will be covered in this lecture. The lecture outline would be Introduction to Chemical Reaction Engineering, then we will consider chemical reactions and its classification, the different variables which affect the reaction rate, then how to express the rate of reaction and their different types of rates, then stoichiometric relationship between the rates of appearance of particular component and disappearance of a particular components in a given reaction. So, those things we will consider. Before going to this lecture, let us understand what are the central topic for chemical engineers. There are 3 important topics for chemical engineers to understand. One is synthesis of materials. As you know, in day to day life we use different materials like our clothes, paste, and starting from all the materials we use every day, they are finished products, but it has produced through a succession of steps. So, from raw material to product, chemical engineers has great roles on producing the finished products. The second thing is the remediation of the polluted air, water and soil. As you know, our air, water and soil are polluted day by day due to different human activities and industrialization. If we consider air pollutions, as you know today, the greenhouse effect, the major pollutants which create the greenhouse effect is the carbon dioxide. We used to hear every day in our newspaper and so on, and we are experiencing a drastic climate change. Water pollutions, as you know, although on the earth there are plenty of waters, major part is the water, but the drinking water or the water which to be utilized are very scarce. So, it's get polluted because of different industrial processes, and we have to make it clean by different means, and similar to the soil pollutions. So, remediation of polluted air, water and soil is another important topic for the chemical engineers to work with. And third is the energy generation. Energy, as you know, this is the one important thing which we need for everything to run. Without energy we cannot survive. So, we need to have enough quantum of energy to be produced so that it meets all the industrial and other requirements. The two main areas we will consider in chemical reaction engineering, one is chemical kinetics and the other one is reactor design. So, in first part of this lecture, in this module, we will consider the chemical reaction kinetics, and later part we will consider the reactor design part. So, motivation for understanding chemical kinetics and reactor design, because as you know, this only subjects which distinguish between the chemical engineers to the other engineers. As we know, reactor is the central features for most of the chemical processes, and even if the separation cost dominates, the reactor often determines the separation cost. If the reactor is efficient and produce product which are of high purity, then its separation may not be required after the product is formed. So, the separation cost in that case would be minimum, but if the reactor is not efficient enough, so that the product which will produce have to be separated, and that separation cost might be much higher compared to the overall reactor cost. So, inevitably these chemical reactors are the central feature for any chemical industries. Chemical reactions are ubiquitous in nature and in industry, as you know. So, this course will construct the mathematical description of chemical reactions and chemical reactors. So, it will represent the chemical reactions and chemical reactors in mathematical form, which we call the design equations or the modeling of rate or rate of reactions or the reactor design or modeling of reactors. So, we will construct the mathematical description, that means the physical system is represented in a mathematical form, and this will allow us to predict and understand the behavior of different reactions and reactors. Every chemical industrial processes is designed to produce economically desired product from different starting materials. Let us take an example. Suppose if you have raw materials, and these raw materials may not be fed to the chemical reactor, it needs some physical separations. So, it should go physical treatment steps. Then once it goes via the physical treatment steps, it will be fed to the chemical reactors. So, chemical treatment steps. Once the chemical treatment is done or it is fed to the chemical reactors, the reactions should take place and it will produce the products. The product may not be pure. So, the products which will produce, that again will go to several physical treatment steps. And then you will get the product. So, once physical treatment steps is followed over here, the raw material which is not converted is again fed to the physical treatment steps, so that it is again fed to the chemical treatments. So, this is recycle. So, this physical treatment steps means once the product is produced, that has to be separated or some purification has to be done, so that we can get the finished products. The physical treatment steps will not be covered over here, because this is already covered in your mechanical operation course or the unit operation course, where most of the physical treatment steps have been considered. Like you have seen in your mechanical operation course, the different physical separations which we used to do in our labs. One is the different types of crusher, where you take ores from the industries, big chunk of ores, and then you crush into different small fractions. That is jaw crusher, roll crusher, and different types of crusher. Again you can also reduce the size in a ball mill or hammer mill, and then you can separate them by different other physical separation steps, like you can have screening of the materials, or you can have froth flotation, cyclone separation, so many other physical separation steps. So, that will not be covered over here. So, here we will mostly consider on chemical treatment steps. In chemical treatment steps, it may be a simple reactor or simple tank, simple mixing tank, but although it is simple, but this is what makes or breaks the process economically. So, although it looks simple, but this is the heart of the process. That means this economically makes or breaks the process. So, design of chemical reactors is not a routine matter. There are many alternatives may be available for a reactor design. So, in searching of the reactor design, one must have to optimize for the cost. So, in one design may be superior with respect to the other design. So, the cost of the overall process have to be considered while designing a chemical reactors. So, design of a reactor is not routine matter. Many alternate may be proposed. For optimum design, one must consider the overall cost of the process. Reactor design uses the information from variety of sources like thermodynamics, it also uses the chemical kinetics, fluid mechanics, heat and mass transfer, and so on. Let us start with what is chemical reaction. A chemical reaction is a process in which at least one species is transformed into chemically different species. Let us consider combustion of methane. This is a very highly exothermic reaction. CH4 methane react with oxygen and it forms carbon dioxide plus water vapor. So, in these reactions, as you can see, the reactants is methane and oxygen and it produce the different compound, that is carbon dioxide and water. But as you could see, the number or type of molecules may change. That means, you can see that the total type of molecules, earlier we had methane and oxygen, which is converted to carbon dioxide and water vapor. So, the type of molecules has changed after the chemical reactions. However, their constituents or the building block materials remains the same. That means, before the reactions, the reactants had 4 methane. So, the hydrogen 4H and after the reactions you could see also 4H. Before reactions we had 1 carbon and after the reactions we have 1 carbon. Before the reactions we had 4 oxygen atom and after the reactions we have 2 and 2 over here. So, 4 O. So, that means the elements or the building block materials that remain same before the chemical reactions, but after the chemical reactions, but the molecular or the number of molecules or the species have changed before the reaction and after the reaction. Now, to find out what a chemical reactor able to do, let us consider a chemical reactor. And you have input to the reactor and you have output and in between inside this is your reactor and you need to know the contacting pattern inside the reactor. That means the reactant materials when it is fed to the reactor, how they contact, how they flow inside the reactor, whether they are well mixed with each other or whether they are segregated from each other, how they flow, what is the contacting pattern inside the reactor. Similarly, we should also know the kinetics of the reactions, whether the reaction is very fast or if it is very fast, then the equilibrium will tell us what the product will produce. Similarly, if the reaction is very slow, then the chemical kinetics or the rate of reactions would tell us what would be the chemical kinetics for that reactions. So, all these informations we need to know when a raw material is processed inside a reactor to obtain output, and we have to find out the relations between the input and the output. So, the equations which would relate between the input and output is known as the performance equation. So, we can write output is a function of input kinetics and contact pattern. And this is known as performance equation. Now, why this performance equation is important? Because this is the expression we can compare different designs and conditions, and from that we can find out which is the best one and then scale up to the larger units. While discussing, we will consider three idealized reactors. Let us introduce a little bit. You have batch reactor like this, where you dump the material and stir it. There is no input and output, we call batch reactor. Then you have flow reactors, one of them CSTR, where you feed the material, stir it, and there is a constant output from the reactors. This is called continuous stir tank reactor. This is CSTR, this is batch, and another idealized reactor is the plug flow reactor. We will discuss more about this idealized reactor later. Plug flow reactor, and from the performance equation, or for a particular reaction to happen, we can, and under the different conditions, we can compare these three reactor design, which one would be best among them, and then how to scale up that to the larger unit, that we can discuss or we can get from the performance equation. And that is why it is very important to design a reactor based on the mathematical description of that reactors, which is the performance equation. Now, classifications of reactions. There are many ways we can classify chemical reactions. The one general type of classification is there are three types of reactions. One is decomposition reaction. That means a reactant would be converted to product. So, reactant A decomposes to produce product P. For example, if we consider ethane CH3 and it decomposes to hydrogen and ethylene. So, this is one of the example of decomposition reaction. The second reaction is combination reaction. For example, if we take reactant A plus B and it produced product P. So, A combined with B produces product P. For example, if we consider nitrogen react with oxygen produced nitric oxide. So, this is one of the example of combination reactions. As you know, this is one of the famous examples of atmospheric nitrogen fixation reactions. The nitrogen in the atmosphere during heavy lightning, it reacts with oxygen at high temperature and produce nitric oxide, and then it converted to nitric oxide, and the nitric oxide again falls with water and forms nitric acid, which again calcium carbonate reacts with nitric acid, forms calcium nitrate, and then it is converted to different usable form of for the plants. So, this is one of the famous example of atmospheric nitrogen fixation. The third type of reactions is the isomerization reaction. That means a compound, say cis A forming to trans A. So, cis trans isomerization of a particular compound, like if we consider cis butene C double bond C and CH3 H. Cis means the methane same group on the same side. So, this is cis butene and this converted to trans. So, here this is 1, 2, 3 and 4. So, this converted to C double bond C, CH3 H, H, C, H3. So, 1, 2, 3, 4. So, this is trans butene. So, most of the chemical reactions can be clubbed into these three types of reactions. In chemical reaction engineering, the best way to classify the chemical reactions is to how many phases are involved for the chemical reactions. So, in view of this, the chemical reactions are classified into two categories. One is homogeneous reactions, that is the reactions takes place in one phase, and the other one is the heterogeneous reaction. So, homogeneous reaction and then the second one is the heterogeneous reaction. The homogeneous reactions can also be catalytic or non-catalytic process. So, we can again distinguish both the processes catalytic and non-catalytic. Most gas phase reactions are non-catalytic in nature. And most liquid phase reactions are catalytic in nature under homogeneous reaction conditions. The heterogeneous reactions, for example, under non-catalytic is burning of coal. As you know, for the energy generation, most of the power plants they uses coal as a main source of their energy productions. So, they burn coal and produce energy and it generates huge amount of carbon dioxide released to the atmosphere. So, gas liquid absorption, with chemical reaction. Here in the catalytic process is ammonia synthesis, oxidation of sulfur dioxide to sulfur trioxide. As you can see, all these are require two phases. In case of burning of coal, it is solid and gas. Then gas liquid is a gas and liquid two phases. So, these are non catalytic process and these are the catalytic process. Haber process for ammonia synthesis is one of the very important example of catalytic heterogeneous reactions. Different variables which affects the rate of chemical reactions, as we have classified the reactions into two categories based on the number of phases involved. One is homogeneous reactions, another is heterogeneous reactions. If the homogeneous reactions, that is reactions takes place in single phase, then the variables which would affect the rate of chemical reactions are temperature, pressure and composition. So, for homogeneous system, the variables are temperature, pressure and composition or concentration. For heterogeneous system, that is more than two phases involved, it becomes more complex, because when we consider say gas solid heterogeneous reactions, the particles are porous, the reactions take place on the solid surface of the different catalyst materials. So, the solute molecules or the reactants has to travel through the solute to the catalyst particles to react on the active sites. So, this depending on the pores and the structure of the catalyst, it creates different mass transfer limitations. In addition to that, suppose the reactions is taking place on the catalyst surface or inside the porous structure of the catalyst, the heat generated, if it is very exothermic process, the heat which would generate due to the chemical reactions, how fast this should release or this should transport to the outer surface, it depends on the structure of the catalyst. So, it also affects the rate of chemical reactions. So, in addition to the parameters which affect the heterogeneous system, it also affects, in including those parameters, it also required the heat transfer effect and the mass transfer effect in case of the heterogeneous reaction. So, for in case of heterogeneous reaction, in addition to temperature, pressure and composition, we need to consider heat and mass transfer effects. So, how to define the rate of reactions in meaningful way? So, to answer these questions, let us have different definitions of rate of reaction. One is based on unit volume of reacting fluid. That is Ri is rate of reaction is equal to 1 by V dNi dt, that is moles of I formed divided by volume of fluid into time. If it is the reactions which is happening in the solid phase, then we can define based on unit mass of the solid in the fluid solid systems. So, based on unit mass of solid, we can write R I is equal to 1 by S d n I dt, which is equal to moles of I formed divided by surface area into time. We can also define based on volume of the solids, unit volume of the solid. So, we can write rate is equal to 1 by V s, that is volume of solid, d n I divided by d t. So, which is the moles of I formed divided by volume of solid into time. We can also define in terms of the volume of the reactor. So, we can also write in terms of the volume of the reactor. So, where we can define R I 1 by V R d n I by d t, which is equal to moles of I formed divided by volume of reactor into time. So, these definitions you will get in the chapter 1 of Levenspiel book, and just I am highlighting over here. So, these are different rates and we can relate among them, like volume of fluid into R I would be mass of solid into R I dash which would be equal to surface of solid into R I double dash and so on. So, this way we can define the rate of reactions. The rate of reaction is a measure of change of concentration of reactants or products over time. So, we can define the rate of reaction is a measure of change of concentration of reactants or products over time. Suppose if we consider the reaction twice NO2 gas which is forming twice NO gas plus oxygen gas. We can write various rates. R1 is equal to minus delta NO2 concentration change of NO2 or mole change of NO2 by delta T. Similarly, we can write R2 delta NO concentration of NO delta T, or we can write R3 is delta concentration change of oxygen divided by delta T. And we can relate these three rate stoichiometrically. For homogeneous reaction, that means the gas, liquid or solid, whatever may be the phase, the rate units are the concentration per time or moles per volume per time. If it is heterogeneous reaction, then that is at solid surface. In that case, we can define moles per area per time or surface concentration per time. This rate is an intrinsic property rate is an intensive quantity, That means, the dependence of the rate is not there with respect to the size of the reactors, that is, the reaction rate is independent of size of the system. Sometimes also we refer to extensive rates, that means the intensive rate is multiplied by the volume of the reactor. How rate can be measured? So, we can measure the rate at three different ways. One, that is at the beginning of the reactions, that is which is called the initial rate. Secondly, we can also measure the rate of reaction at any point of time of the chemical reactions to progress. So, we call it instantaneous rate. And then the third way we can do over an interval of time, where we calculate the average rate. Initial rate and rate loss. Initial rate means the rate of change of concentration of reactant and product in the initial, very initial stage, maybe in first minute or few seconds, that is the initial rates when the reaction starts. So, initial rate is basically the change of concentration of reactants or products as a function of time, measured within minutes or seconds. So, this initial rates allows us to determine the rate law, and rate law is the mathematical representation of the dependency of the reaction rate with the change of concentration. So, at a particular temperature. So, this initial rate allows us to obtain rate law. Now, let us consider instantaneous rate. The instantaneous rate can be calculated from the temperature concentration, from the concentration time plot, that means the variation of concentration with respect to time plot, and if we plot a tangent at any point on the concentration time curve, from the slope of that tangent we can calculate the instantaneous rate. Suppose this is your product concentration and this is time, is like this. So, we can plot a tangent at any point, say at time t1. The slope of this curve can be obtained this means this is your delta p if this is product p, and this would be delta t, that is time. So, the instantaneous rate would be equal to delta P by delta T. That means the rate is calculated from the slope of the tangent at any point of concentration versus time curve. So, this is the instantaneous rate. Now, let us consider the average rate. Average rate is obtained from the change of concentration over a longer period of time. So, this is obtained from the change of concentration over a longer period of time. Now, let us consider an example. Suppose the reaction of nitrogen dioxide, that is twice NO2 form twice NO plus oxygen, and the change of concentration was observed in first 100 seconds. Say the change of concentration of NO2 it happens from 0.01 mole per liter to 0.005 mole per liter. So, if this is the change for the first 100 second, then we can calculate minus delta NO2 divided by delta T would be equal to minus 0.005 mole per liter minus 0.01 mole per liter divided by 100. So, it is 0.004 mole per liter divided by 100 seconds. So, it would be 4 into 10 to the power minus 5 mole per liter second. Now, in the next 100 second, the change of concentration is from 0.005 mole per liter to 0.004 mole per liter. So, this is the change of concentration in the next 100 seconds. So, then we can calculate minus delta NO2 delta T would be equal to minus 0.004 mole per liter minus 0.005 mole per liter divided by 100 second. So, this would be equal to 0.001 mole per liter divided by 100 second. So, this will give 1 into 10 to the power minus 5 mole per liter second. So, as you can see, the change of concentration when the concentration of nitrogen dioxide was more, the rate of change becomes more. That means about 4 times higher compared to the next 100 second. This happens because the concentration of the reactant drops over the time. So, the average rate will obviously be much less compared to the initial rate, because the instantaneous rate is gradually changing because of or gradually decreasing because of change in concentration. Now, let us look into the speed of chemical reaction. As you know, there are some reactions which occurs very fast, like if we consider the reactions of petroleum production, that is production of the gasoline from crude oil, or we can consider the productions of plastics, that is the polyethylene production, the reaction is very fast. Whereas, in some reactions like biological reactions or wastewater degradation or treatment of wastewater, that takes quite longer time for the reactions to happen, very slow reactions. So, if we look into the overall scheme, so as we said, the fast reactions and slow reactions, and in between you have moderate reactions, fast, moderate and slow. So, to look into this, let us see how the reactions can happen, for what systems have higher reaction rates and which system has lower reaction rates. So, different order of the reactions, that is the speed of the chemical reactions, are shown with respect to 10 to the power some exponents. If we look into the reaction rate in case of the cellular reactions or wastewater treatment systems. So, wastewater treatment and cellular reactions, those are in the order of 10 to the power minus 4 to 10 to the power minus 3, in this order. If we look in the human systems, when their working conditions, they are in the order of close to 10 to the power minus 2. For catalytic reactions, they are in this range. Now, if you consider the reactions of different engines like jet engines and rocket engines, those are very fast. Those are in the order of 10 to the power 3 to 10 to the power 4. So, they are in this high speed reaction region, and some of the bimolecular reactions or gas phase reactions at higher temperature the reactions happens to be very fast, which is in the order of 10 to the power 9 to 10 to the power 10. So, in this range. So, this shows the rate of chemical reactions which occurs at different systems. Now, let us consider an examples where the rate of reactions is very fast. So, an engine burns a stoichiometric mixture of liquid, that is liquid fuel hydrogen and liquid oxygen, and it happens in the combustion chamber, and then the chamber is cylindrical dimensions, that is 50 centimeter long and 40 centimeter diameter. The combustion process produces 90 kg per second of exhaust gas, and we need to find out the rate of reactions of hydrogen and oxygen, and it is assumed that the combustion process is complete. So, as per the problem given, we can just draw the combustion engine or combustion chamber, where we have where product is coming out after the combustion. So, we have hydrogen, we have oxygen inside, and its length is 50 centimeter, and this dia is 40 centimeter. And as per the problem given, we need to find out minus R H2, the rate of reactions of hydrogen, which reacts with oxygen and produce the water vapor. So, this is the rate of reactions would be 1 by V d N H2 dt, and minus R O2 is 1 by V d N O2 dt. So, these two we need to calculate. So, let us calculate the volume. So, the volume for this combustion chamber is equal to pi by 4 into d square, d is 0.4 meter. So, into L is 0.5 meter. So, this will give around 0.0628 meter cube. So, this is the volume of the combustion chamber. Now, let us look into the reactions which is happening. The reactions between hydrogen plus oxygen forming H2O. Now, if we write the balanced equation, hydrogen half oxygen will produce H2O. Now, the molecular weight of this is 2 gram, this is 16 gram and this is 18 gram. So, we can calculate the dNH2 dt, that is the hydrogen produced per second. Which is equal to 90 kg per second into 1 kilomole by 18 kg. So, which is equal to 5 kilomole per second. That means, the combustion process produces 90 kg of the exhaust gas. So, our exhaust gas is water vapor. So, its molecular weight is 18. So, we can calculate, as we can see, 1 mole of hydrogen can produce 1 mole of water vapor for this combustion reactions. So, hydrogen production rate would be 5 kilomole per second. Whereas, from the stoichiometry, if we look into that, half oxygen produce 1 mole of H2O. So, D NO2 dt would be the oxygen hydrogen reacted per second would be 2.5 kilomole per second. So, then we can calculate the reaction rate of hydrogen minus R H2 would be equal to 1 by V into dNH2 dt. If we put the values of the volume, that is 1 by 0.020628 meter cube into 5 kmol per second. So, this would be 79.62 kilomole per meter cube second. Similarly, we can obtain the R O2 would be just half of this rate of reactions of hydrogen. So, it would be 1 by 0.0628 meter cube into 2.5 kilomole per second. So, this would give 39.81 kilomole per meter cube second. So, if we write this in terms of the mole per meter cube second, So, this would be equal to 7.962 into 10 to the power 4 mole per meter cube second, and this would be 3.981 into 10 to the power 4. So, as we can see, the order of the reaction rate is of the order of 10 to the power 4. This is the fast reaction. Now, let us take another example of slow reaction. A human being of 50 kg weight consumes about 5000 kilojoule of food per day, and assume that the food is glucose and that the overall reactions is represented by this. That means, glucose reacts with oxygen and produce carbon dioxide and water, and it is exothermic reactions. So, it releases the heat delta H twice 2816 kilojoule. So, if this is the case, then we need to find out moles of oxygen used per meter cube of a person. Given the density of man is equal to 1000 kg per meter cube. So, we need to calculate moles of oxygen used per meter cube of a person having density of man is 1000 kg per meter cube. So, what we need to find out? RO2 is equal to minus 1 by V percent d NO2 dt, that is mole oxygen used per meter cube of person per second. This we need to calculate. Given that density is 1000 kg per meter cube. So, the volume of the person we can calculate weight of the person, that is 50 kg divided by the density 1000 kg per meter cube, which is 0.05 meter cube. Now, as we can see, the each mole of glucose reacting with 6 mole of oxygen and producing 6 mole of carbon dioxide and 6 mole of water and releasing energy which is 2816 kilojoule. So, now let us calculate d NO2 dt would be equal to 5000 kilojoule per day into divided by 2816 kilojoule per mole glucose into 6 mole of oxygen by 1 mole glucose. So, this will give about 10.65 mole of oxygen per day. Now, if we include this in the equations, that is minus RO2 is equal to 1 by V person into dNO2 dt, we obtain 1 by 0.05 meter cube into 10.65 mole oxygen per day. So, this would essentially give, now if we just convert day to second, so this would be 1 day divided by 24 into 360 second. So, this would be about 2.47 into 10 to the power minus 3 mole per meter cube second. So, you could see that the rate of reactions is in the order of 10 to the power minus 3. So, this is the slow reactions, example of slow reactions which is happening in the human consumptions of the food in human being. So, these examples shows that the slow and fast reactions happen in the different speed. So, thank you for hearing this lecture, and we will continue our discussion in the next lecture.